Thank you very much, Joe, and hello everyone. Yes, I'm Alastair. I'm a game designer based in Norwich in the UK. I mostly make escape room games and puzzle hunt style puzzles, but in this session I'm going to be talking about constraints in puzzle games, and specifically how you can model puzzles as constraint satisfaction problems. Now, this can be a helpful way to conceptualize and formalize the logic involved in a puzzle, and also to assist in creating and testing and solving them, not only to ensure that they are solvable, but they are uniquely solvable. Jagrif did a great talk yesterday where he described how he used an automated solver to test some of the levels in his game, Gentoo Rescue. And it came up with solutions that were perfectly valid within the rules of the game, but used mechanics in ways that he hadn't thought of or anticipated, creating more solutions than intended. So it can be used to check and prevent against that. Now, to do this, I'm going to be doing some live software demonstrations, which are always a bit risky. So fingers crossed the tech works okay. First of all, I'm going to demonstrate a few web-based tools and then a high-level constraint modeling language called MiniZinc. Now, this is an introductory session. My intention is mainly to illustrate some different practical examples of how you could use these tools and perhaps use them in ways that you might not have thought of. All the software I'm going to use is completely free and publicly available, and I'm very happy to share the models which I've made in this talk afterwards. So if you're interested, I absolutely encourage you to download them and give them a go yourself. Okay, so every game has constraints. The rules that structure the game define the play area, the set of actions that players are allowed to take, the victory conditions, etc., etc. If you're a parent or if you've ever played games with young kids who try to cheat the rules, you might have uttered that line about, hey, rules make the game more fun. It's the constraints that provide fairness and challenge. And some players choose to impose additional constraints on top of those originally intended by the developer, which is what you find in the speedrunning community or other kind of emergent gameplay in other challenge runs. So we see constraints of refraining from using animal tech, not using infinite jumps, or having to be a washing machine or whatever. And for puzzle games in particular, constraints not only provide the structure of the game, but they are often the defining feature of its gameplay. So the objective might be constraint minimization, to find a solution that requires the minimum number of moves or costs the least amount of resources. Or it might be constraint maximization, such as determining which cuts to make in the rope to collect the most stars or get the highest score. But in this session, I'm going to be considering those puzzles where the objective of the game is simply to satisfy a given set of constraints. So the puzzles give you certain constraints, and all the player needs to do is to come up with the solution that sticks to them. Now, perhaps the most common example of constraint satisfaction puzzles are the kind of newspaper games that Dan King was talking about an hour ago. So Nicholas-style grid logic puzzles like Sudoku, train tracks, Star Battle, that can be completed using pen and paper. And one of the distinguishing features of these puzzles is that, unlike a Sokoban or a Rubik's Cube, where players enter a sequence of moves to transition between states, they require no order or recorded history of inputs. The complete state of the puzzle at any point can be expressed as a static configuration. Now, for a Sudoku, that configuration is a 9x9 matrix of integer values between 1 and 9. And it's common to think of constraint satisfaction problems of only being applicable to numeric values. But if we consider a slightly broader interpretation of what a constraint satisfaction problem is, we can find plenty of games that can be modeled using CSPs. And I'm going to demonstrate that using examples from 3 video games that have been released in the last 6 months, Lingo, Blueprints, and Is This Seat Taken? These are all great Thinky games, and if you're not familiar with them already, I absolutely encourage you to go out and play them. But this is a spoiler warning, I will be talking about some mechanics from these games, as well as showing some solutions to early game puzzles from each of them. Now, if you've played any more than about 20 minutes of any of these games, you will likely have already encountered and solved the puzzles I'm going to talk about, but I don't want to spoil anyone's experience. So if you don't want to risk seeing that, please do not continue to watch. This is your opportunity to step away from the screen. Now, the reason I chose these games is that they're going to provide me an opportunity to talk about constraints across 3 different domains. So we've got language, spatial, and logical constraints. Now, I've said constraint satisfaction problem a few times already, so before going any further, I suppose I should give a definition of what I mean by that. And this might seem a bit abstract and theoretical, but please don't worry. Very shortly, this talk is going to become a lot more practical. So let me just talk you through this briefly. All this is saying is that in a constraint satisfaction problem, you've got a bunch of variables, x. You've got x1 up to xn, each of which can be assigned a value from a corresponding domain, d1 up to dn. And you've also got a set of constraints that define relations between the variables. Now, we have an evaluation, which is an assignment of some number of variables in the set x to a value from their corresponding domain. It's an attempt to solve the problem. And we can say that an evaluation is consistent if those assignments do not violate any of the constraints. And we can say it's complete if all of the variables are assigned a value. Now, if you have an evaluation that's both consistent and complete, we say it's a solution to the constraint satisfaction problem. And that's what we're going to be searching for. Now we've got the theory out of the way, let's get on with the good stuff with some practical examples. And as I mentioned, because constraint satisfaction is often thought to apply only to numbers, I thought I'd start with something completely different and look at how you can use CSPs to model language puzzles using Lingo 2 as an example. So in Lingo 2, you have clue panels that give you a word and one or more symbols that denote transformations that have been applied to that word. And you need to type in the solution, which is the result of applying those transformations and is itself also a word. Now, those transformations may relate to the semantic meaning of the word, its construction, its pronunciation, or lots of different aspects. So although it might not sound like it, this is an example of a constraint satisfaction problem. We have a set of 5 variables, these placeholders at the bottom. And those variables need to be assigned values from a finite domain, which are the letters of the alphabet from A to Z. And we have constraints that the letters assigned to those variables must spell a 5-letter word, and that that word must be a synonym for the word feel. So what we need is a model that can express those variables and constraints in a format that a solver can evaluate. Now, if you've played many word puzzles or puzzle hunts, you'll probably be familiar with the website OneLook. And OneLook is a great online dictionary with a pattern matching function. So we could search OneLook for synonyms of feel that are 5 letters long, like that. But when we do so, it turns out there's actually quite a lot of them. There are too many solutions that satisfy the constraints. We could say that the puzzle is under-constrained. And it's unsatisfying for a player to just have to guess between a number of equally valid solutions. Now, one of the reasons why it is under-constrained is because there's another constraint in Lingo that I haven't mentioned yet, which is that you can only enter words spelled using a bank of letters that you've collected in the game. Now, in CSP modeling terms, we're constraining the domain of values that can be assigned to our variables. We're no longer allowing any letter from A to Z, only those shown on the keyboard. And although one look lets you specify some constraints on the general pattern of the word it needs to find, it doesn't allow you to specify only a subset of letters. So we need to look for another solver. So let me introduce you to one of my favorite puzzling tools, which is called CAT. CAT is a constrained word finder that's very popular among cruciverbalists and puzzle hunters. It's created by Mark Owen, who sets crosswords under the pseudonym Chronopolis, and it's available on his website. Now, compared to the simple pattern lookup that you had in OneLook, CAT lets you write quite sophisticated constraints on both the morphology of a word, the way it's constructed, and also its semantics, what it means. Now, as is often the case with tools that are powerful, it does come with a modified degree of complexity, but it does have a very thorough help page, which you can look at here, which shows lots of examples of the functionality and the syntax required to use them. So looking back at our Lingo example here, if we wanted a 5-letter synonym of the word feel, we can express that in CAT using syntax like this. So what this says is that we want a string of 5 letters that is formed from some jumble of the letters RTUI-OHCN, which were the letters on our keyboard, and the resulting solution appears in a thesaurus as a synonym for the word feel. And when we click search to execute that, we get now just a single result, which is the word touch. And just in case you have any doubt, that indeed is the answer. Now, another powerful feature of CAT is that it can find sets of words that simultaneously satisfy a set of constraints, somewhat like a simultaneous equation. So on this clue panel here, we want to split the word mailbox into 2 words, mail and box, and then we want to come up with a 5-letter word that can precede both of them to create specific subtypes of each. Now, back into CAT, we could express that using syntax like this. So in this example here, I'm using the capital letter A, and capital letters in CAT are variables. So this is a pattern of some number of letters. I've put vertical bars either side of it to denote the length of that string, because I want to have a string of length 5, and that's going to represent the word we're looking for. Then I want to be able to prepend that 5-letter string onto the beginning of mail and box to come up with 2 new words. And when I search for that, I find that I actually have 2 examples of solutions that meet that set of constraints, which are down here. Now, at this point, I'm faced with a bit of a dilemma, because I could just keep going and tell you how brilliant I think CAT is for solving these kind of word puzzles, and how it can be used to solve more complex and sophisticated language constraints that are used in the game. But I also don't want to spoil any more than I already have done. So what I'm going to do is just very quickly show a handful more example panels alongside the syntax which you could use to model those constraints in CAT. But I'm not going to tell you the answer or give away any more mechanics of the game. If you're interested, you can come back and pause these slides at the end to study them in more detail, or else I'll be very happy to chat about these in detail afterwards. And if you do enjoy language puzzles, as well as some very interesting non-Euclidean sort of level design, I strongly encourage you to check out Lingo. Okay, let's move on and talk about creating constrained word puzzles. So this is an example from the Dash puzzle hunt, which was a set of cards with 2 pictures printed on them. The image on the top is an anagram of the thing on the bottom, but with 1 letter added. No, sorry, the thing on the bottom has had the letter added. So this is sometimes called a trans-deletion puzzle. So, for example, here we have a boar and a cobra. Here we've got a crab and a cobra. And if we wanted to use cat to solve this puzzle, let's just pull it back up again. So let's have a look at one of these cards. Up at the top here, we've got an ostrich and whatever that is. Let's find that out. So I want to do an anagram of a letter bank formed from the word ostrich and then any other single letter, which I can do with a full stop. Let's search for that. Oh, it's chariots. Yeah, okay, so these are chariots. But suppose we want to do it the other way around, which is that we're creating a puzzle with a message that we want to encode, and we need a set of pairs of words that differ in the specified letters that spell out that message. Well, we can do that with the equation solver mode as well. Let's say that we want two words that only differ in the single letter A. So we have a word which is formed from two patterns, A, B, and we want to be able to sort of split the word at that point between the A and the B, insert an A, the letter A, that is, and get a new word. So this is our constraint pattern here. What this is saying is find me two words that differ because the second one has had an A inserted into the middle of it. If I search for that, well, we actually get an awful lot of results, so many, so that in fact the search gets terminated after 1,000 results. Now, one of the reasons for that, and also one of the reasons why some of these results are a little bit obscure, is because we're currently searching in the UK Advanced Cryptics Dictionary, which has got about, I think it's about 250,000 entries. So we can choose a different dictionary to search in instead. Most of these dictionaries are in English, but I should mention that CAT also has a French language dictionary available as well. If I search for in PDL, so this is the Public Dict Large, I think it stands for. It's like a Unix dictionary. It's got a lot fewer entries. It's got about 37,000 entries, I think. And they're also all reasonably common words. So what we're doing by changing the dictionary, again, we're further constraining the results that we get because we're only going to be looking for solution words that appear in this more constrained dictionary. And now we've got some more common words. So we've got on this side, you've got the word cot, and you can add an A to get coat. We've got pint, which you can turn into paint. Cost becomes coast, things like that. And you can repeat this process to get pairs of words for each letter in the message you want to spell. I'm sure you can imagine lots of ways you could use this kind of mechanic to spell sort of a riddle type game. All right, let's move on to something completely different and take a look at blueprints. Now, I imagine most people watching this will be familiar with blueprints, but if not, let me briefly explain one of the early puzzles in it, which is the parlor game. So in this game, there are 3 boxes on pedestals, and each box has a statement written on top of them. In this example, the blue box says this box contains the gems, the white box says it does not contain the gems, and the black box says the other 2 boxes are true. Now, if all those statements were true, this would be a very easy puzzle. The gems are in the blue box. However, there are some more constraints which are written on the desk over here. At least one box always tells the truth, one box always lies, and there's only a single box with the gems in it. And we get one chance to open a box trying to find the gems using this key on the desk. So you might recognize this as a version of a classic knights and knaves problem, or one of Raymond Smullyan's many variants on it. And the way you might approach solving this puzzle manually is to pick a box and assume the statement on it is true. So let's start with the blue box, which says that it contains the gems. If that were true, then the white box statement, which reads that this box does not contain the gems, would also be true because they're in the blue box. And if both the blue box and the white box statements are true, that would make the statement on the black box true. But this would fail to satisfy one of the constraints, which is that at least one of the boxes is false. So we have an evaluation that is complete. We've assigned values to all of them, but it's not consistent because we've broken one of the constraints. Now, we based this evaluation on the assumption that blue was truthful. So now let's try assuming that blue's statement is false instead. Now, if that's correct, we know that the gems are not in blue, but they could still be in either white or black. Now, black states that the other two boxes are true, which is now no longer true because blue is not. So we've identified two false boxes, blue and black, but there's a constraint that there must always be at least one box that displays true statements. So we can assign white's statement as truthful. So white is truthfully stating that it does not contain the gems. Blue is lying that it does contain the gems, so they must be in black. We've got a solution from our assignment of values. We've assigned a value to everyone, so it's complete, and we've not broken any constraints, so it is consistent. That is our solution. Now, let me show you how you would model this same approach using a constraint modeling language called MiniZinc. So MiniZinc is free and open source. You can download it from minizinc.org, and it looks a little bit like this. So it's a general purpose constraint modeling language. Compared to the syntax in CAT, which I was using for the Lingo puzzles, it might feel a little bit more like programming. But the point is that you don't have to write a program to solve the puzzle. All you need to do is to learn the syntax of how to describe it. So here is a MiniZinc puzzle of the exact blueprint parlor puzzle I just showed you. Let me step you through what each line means. First of all, we define an enumeration of boxes. So we've got our three boxes, blue, white, and black, in the order they appear. This is just a named list of things. And it means that from now on, we can refer to the boxes by their color, which just makes the model easier to read. Then we say how many statements there are on each box. So in the example I showed, each box only has one statement, but that can change. It can be anywhere from 0 to 3. And we state that as a fixed constant assigned as part of the puzzle setup. And then this is where the real kind of the meat, the real action happens. These are decision variables. So in constraint programming, a decision variable is something whose value we don't know. And the solver's job is to find values for it that satisfy the rules that we're about to define, the constraints. The keyword var here doesn't just mean it's a variable, as it might do in some programming languages. Rather, it's a variable that the solver decides. So we've got two of these. We've got statement true, which is an array of Boolean values, true or false, that records for each of the possible statements of the box, up to 3 of them. For each of those, is that statement true or false? And then we have another decision variable, has prize, and this is a single array of Boolean values that records which box has got the gems in it. Okay. And rather than us reasoning through the puzzle ourselves, we give these unknowns as part of the model to the solver and let it work out the consistent truth values in a very similar process to we did manually, but it's going to do it for us in a slightly smarter way as well. Then we have the global constraints of the puzzle. So these were the rules that were written on the piece of paper that we found on the desk, and these apply to every example of the parlor box puzzle. The first one was there is at least one box whose statements are all true. And this is what we call an existential constraint. It says that there must exist amongst all the boxes, there must exist a box B for which all of the statements on that box, from 1 to however many there are, that statement is true. So the outer brackets here, the outer parentheses, say that there is at least one box, and for that box, we have a for all that says all its statements are true. And altogether, what we're saying is it's at least one box that's completely truthful. And hopefully you can sort of begin to see how expressive this kind of syntax for modeling constraints is. All we're really doing is re-expressing exactly the same rules that we were given as a human player in the game, but in a logic that's, slightly more formalized, although still pretty close to exactly the same meaning. I haven't had to write anything with for loops or, if else statements. I'm simply translating each rule one at a time into a constraint. This one here, well, this is the parallel constraint to this one that says that there must be a box somewhere amongst all the boxes for which all of the statements on that box are false. This was the second constraint we were told. And then finally, we know that there's exactly one box that has the gems in it. Now, we defined has prize as an array of Boolean values. So what we do is we first convert those Boolean values into an integer using bool to int, where true is 1 and false is 0. And then if we sum all of the integer values, 1s and 0s, we only want there to be one that's truthful. So we want the sum across all of the boxes to be equal to 1. That's just saying that there's exactly one box with the gems in it. So all I've done here is formalize the rules of the game that were written on the sheet on the desk. What we then need to do is to translate these statements on the boxes into constraints as well. So that's in the next section. Oh, sorry, I've just lost my slide. Let me just get that back. There we go. Try and pin that there. For the examples, which I showed you, first of all, we had just one statement on each box. And the statement on the blue box said, this box contains the gems. So when expressed as a constraint in MiniZinc, we turn that into syntax that looks like this. And what this is saying is that the first statement on the blue box being true is logically equivalent to the blue box having the prize. So this symbol here, you might not be familiar with. This is logical equivalence. It's saying that the two things either side of it always have the same truth value. It's stronger than just saying, if this is true, then this is true. It's literally saying if and only if. It's an equivalence. The white box had a similar statement, except that here we have the negation operator as well, because the white box said this box does not contain the gems. And if that statement is true, the equivalent truth value is that the value of house price for white is false. So we invert it there. And black had the statement that said the other two boxes are true. So this introduces an and. This is a logical and we've got here. And if the statement written on the black box is true, then that is logically equivalent to saying the statement on the blue box is true and the statement on the white box is true. So again, all we've done really here is just convert one step at a time, just retranslate into a different syntax each of the constraints that we were given. And now what we can do is we can hit the run button, and 79 milliseconds later, we get the answer, which is exactly the same answer as we worked out ourselves through the manual process here, that the gems are in the black box, and it's given us the truth values of each of the statements written on the box. Now, again, as with the previous example, I've got lots and lots more examples, which I'm very happy to share with people later if you want to try running this yourself. I think it's a really, really interesting. Sometimes I think, trying to write programs to solve puzzle games is nearly as interesting as trying to solve the puzzles themselves. It's a great way of really understanding how the puzzles work. I just wanted to show one more example. I should mention that I've numbered the puzzles here, but this numbering system is slightly arbitrary. As far as I'm aware, they appear somewhat selected from a random pool in the game. But the one that I've called Puzzle 5 here is an example where there's more than one statement on each box. So there's actually two on each box in this one. And what we've got here is that the first statement on the blue box says, this is not an empty box. Well, we can, that's the same example. Saying this is not an empty box is the same as saying this box has the gems, because we know only one has. The gems are not in the blue box. This is an interesting example. This statement is true. Well, this is a tautology, because saying that this statement is true is logically equivalent to this statement being true. So that's quite a fun example there. We then got the above statement is false, where we say that the second statement on the white box being true is logically equivalent to the first statement not being true. But when I run this example here, excuse me, I just need to save that first. There we go. We get our answers here. But there's one more thing I want to show you is that there's actually multiple answers to this puzzle. If we come to the configuration editor here, you can see the default behavior is to stop after one solution. But if I just turn that off for a moment and run it again, you'll see that there's actually two possible truth values that the statements can have in this example, but they both resolve to the same solution, which is that the gems are in the same box, whichever of these two logical paths you problem. I just think that's a really interesting example. And I'm not going to spoil any more blueprints, but there's lots of more interesting logical constraints than that come along as well. Okay, it's time to move on. Let's have a look at Is This Seat Taken? Which is a cozy puzzler game that came out earlier this year, and it's about fulfilling demanding clients' seating preferences. Let's just step forward. So here's an example of one of the early levels, which is set on a bus. And I've selected one of the characters here, Annabella, which means you can see her requirements appear at the bottom left. So she can't stand talking, and she can't stand loud music. And each of the characters down here will be fussy in their own unique and sometimes quite annoying way. And you've got to place them all into one of the seats. Remember, that's what makes our evaluation complete, such that their individual preferences are all met. That's what makes it consistent. So the first step to being able to express this in a constraint satisfaction model is to assign a unique index to each of the positions at which characters can be placed. So I've just done that here. This is my arbitrary numbering system, but this is what I'm going to use to refer to in the model. And you might have noticed some different properties that the seats have. Some of them have a window. Some of them are next to the aisle. Some of them face forwards. These four here are standing only, for example. And some characters will demand a seat with one or more of these properties. And we call these unary constraints because they only constrain a single variable, the seat on which that character is placed. But we also get binary constraints over a pair of variables. And what I find quite interesting in this game is the way in which the game translates those constraints into the narrative of the game in terms of spatial proximity and vicinity, because the constraints can sometimes seem asymmetrical. For example, let's say you've got a character that demands they sit with another person that they can talk to. So you might put that person on seat 2 here, for example. And to meet their constraints to talk to someone, you will then also need to place someone on seat 1 who wants to talk to them. Those two characters on those seats are considered with each other, and they need to have that kind of proximity to be able to talk to each other. Now, it doesn't have to be immediately on the seat next to them. So, for example, the seats 9, 10, 11, and 12 are all considered to be with each other. So they have the same kind of proximate constraints as 3 and 4 and 1 and 2 do. All of these 4 characters can talk to each other. But if a character like Annabella comes along who can't stand talking, it's not sufficient that they are just not sat next to someone who talks. They actually need to be much farther away from them. So if 1 and 2 are talking to each other, for example, we can't put Annabella in 3 and 4 or 13 or 16 or 18 as well, because she'll get annoyed by them talking to each other. So we've got these kind of 2 levels of proximity that are defined in the constraints, even though apparently it relates to the same attribute, which is that is this person talking or not, which I think is quite interesting. So let's go back to MiniZinc again, and I'll show you how I modeled this level. So I start off with our 23 indexed positions, the seats on which, or possibly standing room that people can be placed in. And this is where I defined the properties that those seats have. So if I just move that to the side again, you can see the set of seats that are on the aisle. We've got 2, 4, 13, 16, 18, 20, and then we've got these ones at the front of the bus as well. Do they face forward? Are they a standing seat and things like that? So I've placed the indexes of those seats into sets depending on which properties they have. We're literally, again, as with the blueprint example, we're literally rewriting the puzzle into something that's quite close to English, but just a formal way of defining those constraints. Here we've got what I was just mentioning about the spatial proximity between seats. So I've got an array of all of the seat positions, and I'm going to put the index value of what seats they are considered to be with or nearby. And that's what's going to be used for the different constraints that the characters have later. We have our array of characters in the level, and we place them into sets of people, just as we placed the seat positions into sets to say whether they had a window or an aisle seat. Here, so this is Annabella, for example. She's been placed into the set of people who can't stand loud music and the set of people who can't stand talking either. Other characters have got other constraints that they need being met. And the decision variable we have in this case, what we want the solver to come back with, is an array of the positions that get assigned to each person. So it's complete. Every person needs to have a seat so that their constraints are all met. That's what makes it consistent. And we have our constraints written down here. So the first constraint, everyone needs to be sat on a different seat. As far as I'm aware, there's not a bonus level where two people can sit on each other's laps or something. We'll assume not. So we'll put a constraint that all of the values assigned to the seat positions assigned are different from each other. That's fairly straightforward. Then we go through all of the unary preferences that people had, all the unary constraints. So for every person that said they wanted a window, the position assigned to that person has to have a window. That seems reasonably fair enough. And we go through all of the different properties that the seats can have, such that that's the case. Some people mention binary constraints with another specific named character. So Olivia wants to be with Evelyn. And the way we say that, again, it's an existential constraint. So we say that somewhere in the positions that get assigned, there is a seat A such that Olivia is put in that seat and Evelyn is put in a seat that is one of those in the set of seats that is with A. And the same with Winnie and Yuki here. Now, these are particular named individuals, but we can also do that across the sets of people we identified as well. So for everyone, every person that's in the set that cannot stand loud music, and for every person that's in the set that plays loud music, well, the position assigned to anyone in this set can't be nearby a position to anyone that's assigned in this set. So this is a set of binary constraints. It's a binary existential constraints that are applied across groups of people. It iterates over all the pairs of these two groups and just ensures that they're not placed together. And when we get to the bottom, so I can run this model now, here's all my constraints. And we can see actually there's a surprising number. In fact, I'm going to kill that because I'm a bit worried that's going to hog my CPU. I can tell you, because I ran this earlier, that there is actually, hang on, I've got the number written down here. There's 492,120 valid solutions to this level. It actually only takes under a minute on my PC for MiniZinc to enumerate them all, but I was a little bit worried that it's going to lock up and prevent this the stream happening, so I'm not going to do it. But what I can do is come back to the configuration here and say that I want a user-defined behavior that stops after, say, the first 1,000 solutions, for example. And if I just run that, there we go. In 347 milliseconds, you can see all of the different solutions enumerated there. Now, in a game like Is This Seat Taken, it might not matter that there are multiple solutions because the assignment entered by the player is tested in real time in the game to see whether it satisfies the constraints or not. But there are times when you might want to ensure that there is only one valid solution that satisfies all the constraints, either for reasons of elegance or because of other mechanics in the game that mean that you need to ensure that's definitely where the player ends up. So to talk about uniqueness, let me give you another example, which is from one of my own puzzles, which is a kind of a cross between Cluedo and Sudoku. So you have a 9x9 grid of a crime scene in which you must place 9 suspects. And the constraints come from the combination of regular Sudoku or Latin square constraints, so only one character per row and per column, combined with the narrative constraints that they make in their witness testimony. So on interview, a character may give you a unary constraint by saying that they were in a doorway, or that they were facing a window in a certain direction, or that they might make binary constraints about being in the same room as another character or being adjacent to a certain room. And the objective is to place everyone in the scene, determine where everyone was, to figure out who the murderer was. And because this is in a book and solvers compare their answer to a published solution, it's important to ensure that there's only one unique valid solution that meets all the constraints. So this is the model for that. There's reasonable amount to this because I basically encoded all the possible descriptions of the kind of statements that people might make about where they were. So what kind of walls were they in? Were they in the corner? Were they in a room with a certain number of people or things like that? Then at the bottom, we have the level data. And now this has been injected from a Python script. One thing I didn't mention is that MiniZinc has Python bindings so that you can integrate it as part of a workflow. You don't have to actually write everything in the IDE here. And then we have the constraints here. So these constraints at the bottom, these relate to the clues that players will be given to help them place the characters. Now, because of the way that the puzzle is created from the Python script, these are guaranteed to be a logically minimal set. So I can run this here, and I know I will get a single result back. In fact, let me put on output solving statistics there. Just run that again. So you can see I've got a number of solutions is exactly 1 from this set of constraints. So I've got something that guarantees uniqueness, but it's not necessarily human interesting set of clues. Instead of just saying the fewest constraints that ensure uniqueness, you want the fewest constraints that produce the most reasoning variety. And this was a topic that Jagrif mentioned in his talk yesterday as well. So the goal becomes maximizing the diversity of reasoning paths while preserving uniqueness. And that's much harder to automate, and why many of the best logic puzzles are still handmade. So I manually edit all of the puzzles by hand. And suppose I decide that describing character 1 as being in the doorway of a room is not interesting enough. Maybe I've used too many similar constraints recently. I want to mix it up a bit. So what I can do is I can remove that constraint. I'll just comment it out for now. And then if I run the model again, oh, sorry, hang on. Thought I crashed it there for a minute, but it's I just had a pop-up window that I didn't notice. Sorry about that. I've now got 2 solutions. So it turns out that this constraint was actually required to force a unique solution to the problem. But if I don't want to introduce that, I could possibly put something else back in instead. But I need to work out what has become under constrained as a result of removing that. And I can actually print that out here. So if I just scroll this up and compare these two outputs here, what I'm looking for is what character has been able to move as a result of removing that constraint. And you can see it's characters 1 and 7 here. So what I could do is I could put back in a new constraint instead. Let's say constraint is knight from 1 and 7. So that's just saying that in this version, which is the one I want, there's a knight's move between 1 and 7. And if I run that again, we should find that number, hopefully, now has returned back to 1. So this is, it's not an automated way of doing it, but I'm able to use the constraints that I have and kind of iteratively test new ideas and run them through this model each time to check that I'm still got that unique solution. So what are we doing for time? I probably need to go on. This is my last slide. I just want to do a bit of a summary, really, as to some of the things I've shown and why you might want to consider using constraint satisfaction problems to model puzzles. So for solvers, for people playing Thinky games, instead of reasoning through every combination by hand, the solver performs the logical inference automatically. So you just describe the rules, not the reasoning steps. And that's what I was hopefully trying to show in the modeling I was showing earlier. Now, you could, of course, just use a brute force approach to check every possible configuration, but that can grow exponentially and be unwieldy if you've got a large state space. A constraint solver is written to use smart propagation. It prunes impossible cases early and only explores those combinations that could still satisfy the rules. So this means, as you see, in a few milliseconds, it can come back with the results, and you can make models much more complicated than the trivial examples I've shown here. And you don't have to write that smart solver logic. Other people have already done that for you. All you have to do is provide the model. And also, the process of actually stating the model in the right format forces you to be precise. You have to express exactly what each clue means, and doing that often reveals kind of ambiguities or assumptions that you might have had. Even if you then don't go on to use the solver, preparing the data in the format is a great way to understand the problem. Now, if you're someone who creates puzzles, why might you want to use them? Well, once a puzzle has been formalized, you can let the solver verify it automatically. Does it have at least one solution? Is that solution unique? Are the clues consistent? This saves an enormous amount of time when designing new puzzles or testing variations. You can easily tweak constraints, as I just showed in my Cluedoku example there. You can make new versions, just comment out one scenario and enable another. And this lets you explore how small logical changes affect a difficulty or solvability or structure without rewriting your reasoning from scratch. And you can also invent puzzles that would be very hard to reason about manually, or could be prone to you introducing errors in testing them. For example, you could have logic puzzles with recursive truth statements or self-referential constraints, multiple interacting clues, or sort of a probabilistic twists. The solver doesn't care how tangled the logic is. As long as you can define it, it can handle it. And that's what I think is just really beautiful. And for me, I just think it's really interesting way of exploring the structure of a puzzle in a formal way. And yeah, that's pretty much all I've got to say. So I don't know if there's been any questions or not. Hi, Joe.
Hello. There have been many questions. Thank you so much for that talk. I had flashbacks, and you kind of brought back memories of MiniZinc. I had completely forgotten, but in the back of my head, yes, I had learned MiniZinc in the past.
Oh, there you go. Okay.
Yes. And also, I had flashbacks to learning Prolog as well, which you can use to do similar things, right?
Sure.
That actually connects to one of the questions that we had.
Okay.
So I'm not sure, I'm not familiar with this language, but somebody, Feverish, brought up the language lean. I don't know if you've come across that. They're asking whether it can be used for this kind of thing. But if you haven't, then you
I'm afraid I don't know, but I will very happily go and look it up myself. Yeah,
Sure.
I don't know.
Okay.
I'm afraid. Yep.
So I was doing a little bit of looking it up, and it seems to be a kind of language for like proof, like formal proofs.
Okay.
And
yeah, I mean, I will just say I chose MiniZinc. You said you used. I should mention I did not study computer science. I studied something completely different. So I've come to MiniZinc later. It seems to me very well documented. It's very easy. It's well supported, and there are clearly other tools available as well. I mean, Google OR Tools is a very well known one. There's no particular reason I'm pushing people in this direction. I'm sharing what I guess works well for me.
Yeah.
But yeah, there absolutely are others. Yeah.
Yeah. Thank you so much. So then Waika was asking, does one get the same satisfaction using these tools to solve the puzzles as doing it without them?
Oh, that's a great question. You definitely get a satisfaction. Is it the same satisfaction? I mean, yeah, it like I said, it engages the part of your brain that gets yeah, obviously you get the answer in the end, and I guess you don't get the same effort reward of thinking I really earned that. But in a sense, you get a different way. I think it's fun. Yeah.
Yeah. Oh, so I was going to ask you a question which is connected to that, which is when you're playing a Thinky game, do you find yourself like gravitating towards using MiniZinc to solve a puzzle, or do you try and put it off if you can?
Yeah. So I'll be totally honest. I mean, the examples I showed here were almost intended just to. They're not toy examples. I mean, they really are. They really do work, and they solve the puzzles. No, I don't normally have MiniZinc running on one monitor and playing a Thinky game on the other. You could, but no. I'm more like I said. I'm literally just trying to show people examples of ways it could be used, and maybe it just sparks a little something. No, I don't actually use it as a general.
To be honest, there are some games where knowing that this is available and you can do it like this would help you get through some of the parts of the game. And actually, sorry.
Yeah, no, I would. Some of the, and again, I really didn't want to spoil this. I hope no one felt that I've revealed too much. But some of the later blueprints puzzles, I absolutely did use it to verify because I failed them the first time. I can't see how that is. Yeah, when it gets more complicated later, it is quicker to get the answer.
So I was wondering, so we've got Tonda Ross, who made blueprints, is speaking tomorrow at the event, but I don't think he wants to talk about things like that during his talk. But I wonder whether you have any instincts about whether Tonda might have used constraint. Like, it kind of, to me, I've seen some of those later things, and I'm like, it kind of feels like he must have used it.
I'm sure he probably did. Yeah, I mean, that style of puzzle, the logical, truth tellers and false tellers. Obviously, there are many different variations of this. I would be fairly confident in saying he used some sort of automated testing. Yeah,
at least just to verify the
absolutely
correct. Yeah, absolutely. Okay, cool. So we also had a question from Jagriff. Can the solver give intermediate results, i.e. what the options are after one propagation step, after two propagation steps? So this is very specifically about MiniZinc and whether you can do that.
Yeah, so MiniZinc has several backends that you can direct into. So there's Chuffed and there's FlatZinc and lots of other different solvers. And so the exact functionality of what is available depends slightly on what backend you're using for it. Yes, you can look at the domain size after, as the model progresses. And in fact, there is some, if I can get it back up again. Oh, no, maybe I can't actually. There's solving statistics. There's a whole load of solving statistics. You can look at how many, leaf nodes were explored and how many were rejected and how many things like that. So you can't literally do it after each step, I don't think. Not at that level of granularity, but yes, there is more information you can get. And again, you can access that programmatically as well. So if you're looking to kind of change a strategy to narrow down a solution faster, you can tweak things and see how they're affecting the search space. Yeah.
Right. I was thinking that about depending on which backend you use, it might take different steps to get to the answer. So you get very different steps along the way.
Yeah, and you do get some metrics to be able to compare them. Yeah.
Right. Okay. So then just one last question here, then we'll go to the break. Actually, maybe with two last questions. So you were talking about potentially using CSP or like modeling puzzles as CSPs in order to help you design them. Would you say there's some risk there of like, well, in order to reason about this puzzle that I'm building, I'm having to model it as a CSP? Does that potentially risk making it so complicated that even your player would have to model it as a CSP in order to solve it?
Yeah, so I wouldn't want to duplicate effort, I suppose, depending on the structure of your, and absolutely CSP does not apply to every Thinky game. I wouldn't want people to think I'm suggesting that. It definitely doesn't. I think there is an advantage to being able to state your core constraints in a format that are independent and that you can just lift them out and put them into a different solver and then bring them back into your game. But obviously, if it gets to the point where you're almost maintaining two copies, then you're introducing a whole load of risks there that I wouldn't do. For my particular games, it's worked quite well because the core model is actually very constrained. If you've got such a tightly constrained, it's such tightly integrated into the rest of your game model that you can't extract the constraints easily, then maybe it doesn't work so well.
Right. Okay. Also, you pointed out that with your own puzzles, you don't just look for some set of constraints that result in a solution. You are also trying to optimize for interestingness. And I liked how you express interestingness as like involving different types of deductions along the way. But yeah, so it's like even when you're using a CSP to help you design puzzles, you can still factor in like what like not just can this puzzle be solved, but is this puzzle going to be interesting for somebody to solve without a CSP?
Yeah, absolutely. And as with so many other things, it's a tool. It's not the answer to everything. I don't think it can automate everything, but there are definitely ways you can use it to facilitate easier development, or perhaps novel ideas that you wouldn't be able to manually iterate on. Yeah,
great.
But give it a go. Like I say, everything I demonstrate is free. You can go and download this. I'll share the models on Discord if anyone's interested to play along. Absolutely happy for people to do that and ask questions there. Yeah.
So if somebody was getting started with this and maybe found the models that you share on Discord, what would you say that one of those is a great starting point, or are there other Thinky games that you think might be even simpler to begin with?
I would say pick something that you personally find interesting, and also ideally that you've attempted to solve the traditional way first.
Sure.
Because I think that will help you understand that translation step of this is how I think of a human to solve it, and this is how I express it to the constraint solver to solve it. Other than that, I think you could pretty much choose any game and give it a try. And almost, as is a lot of the time, you learn more from failing than you do from getting it right first time. So if you try to model it and you realize, oh, that's tricky actually, because how do I express that? And it is just that thing that drives the thought process that can be just as valuable as just it coming out with the right answer.
Absolutely. Thank you so much. We will leave that there. Any further questions, if you want to take them to Discord, thinkygames.com/discord is where to find that. Alastair will be there to answer any further questions that people have. We're about to take another break, I believe. Let me double check. Yes, that's correct. So I'll see you all in 30 minutes. Thank you once again, Alastair.
Thank you.